So I'm Thomas Theunissen. I'm a researcher at the University of Bergen. I work in, it's a work done in collaboration with Ritske Huisman, Delphine Rouby in Toulouse, Sebastian Wolf and Dave May. It has been project initiated several years ago now with the Colors project funded by Total Energies. And all the computation has been done in the framework of Sigma 2, which is the national Norwegian infrastructure for computation, high computation performance. So I'm going to talk about ongoing work we're doing in 3D, where we couple surface processes on extension in an oblique system. I'm just going to focus on one case, but Elisabetta actually mentioned that 80% of the rift system or rifted passive margin are oblique or were oblique during their formation. Here it's a typical case, which is equatorial Atlantic system, basically at a time just after breakup or around breakup time in this reconstruction. On this system is, if I can get arrow somewhere. Can you see an arrow? Maybe not. So I can't get the arrow for some reason. Okay, anyway. So it's segmented. So we have few segments that's separated by a long transform, basically about 300 to 700 kilometer long transform. And they are characterized by different length, but also different length of the segments, but also different orientation of the extensional segments. On each of these transforms have also internal characteristic like transpression that differs. For example, the Romanche is more transpressive than the two others that are the Shannon sample. And we have all these structures, they are more or less aligned with inheritance in the continental domain, as we can see here from the transition from Archean to Proterozoic mountain belt, and also some Proterozoic shear zone. And it can both seen in the two figure here. On what we know on Earth, I mean, we have about 70 to 80 transform margin on Earth. On most of them, at least 60%, they are longer than 200 kilometers. So two questions rise from this observation. What are the conditions for long transform fault initiation during highly oblique continental rifting? On the second question, what are the implications of transform fault initiation on topography evolution, which is a key problematic, especially for the source to sink problem. So where goes the sediments? So in the previous numerical modeling done, so sorry, I don't have the pointer, but so I'm gonna try to be as precise as I can based on the display I have here. So it was different studies before that shows that the lithospheric inheritance is a requirement. So on the left here, by the work from Vanida Alkin in 2012, we see that so it's basically you have two weak seeds, one in the north, one in the south. They are offset. And then we look at the propagation and the linkage between these two propagating rift segments. And it was possible to form a short transform, less than 100 kilometers, maybe between 30 and 60 kilometers, for really a small range of condition, which is a weak continental crust on a relatively weak shear zone. After Taras Geria in 2013 has shown that the mid-ocean ridge might have a role also in the linkage and in the formation of short transform margin, and also shows that this also might control the distal structure of the transform. Then Lawrence Wolf in 2022 has shown that for high erosion efficiency, and also with a strong crust, you might be able to form a short transform in such a linkage system. And then Laetitia Lepourier in 2017 has shown that if you increase the offset between these remote weaknesses, then you would not have any linkage, as you can see on the left here. instead you have two segments, one abundant rift system and one other which is active with no linkage. And if you have a stronger crust for the same offset, you can actually have an oblique linkage between the two segments. But so far, if you increase the offset more than 300 kilometers, you have no linkage. And Derek Neurath has in 2021 shown similar analysis. So on the vertical axis, you have the crystal strength. On the horizontal axis, you have the offset between the two remote weakness. And we see that weaker is the crust, simpler is a linkage. I mean, you can have a linkage on also from some microplate in some place, but for some really small condition, you can form a small transform, but no long transform. You have basically no linkage in the last column if the offset is higher than 300 kilometers. Attila Balat in 2023 has done a model with simple surface processes, so including diffusion for the erosion, but the topography analysis was really limited to a small region along the transform. So there is another type of modeling approach, which is basically using a damage zone instead of using weaknesses, really local weaknesses. And we see that we have rotation of the strain with time. So basically, you start forming shear zones which are parallel, perpendicular to the direction of extension. And then through time, you finally link the system into an oblique fashion, which are parallel to the damage zone. Similarly, Guillaume Duclos has a similar conclusion here in 2019. Showing the rotation of the different structure with strain, but finally having a linkage which is oblique and parallel to the damage zone. And there is another type of inheritance where it's a sequence of weak seeds which are embedded inside the model domain. And that shows that if you have, so that was work by Christophe Basile and Jean Braun, and also one by Anthony Jourdan and collaborator in 2021. And they show that you can form some small strike slip zone and short transform, but finally the only way to form a long transform on a long strike slip fall zone is actually to have inheritance all along, basically the entire model domain. So it means that to form long transform margin, we need inheritance. So, but we still don't know from all these models what are the implications of the transform fault initiation and topography evolution. So just to recap the model approach that we used for people that's not aware about this approach. So we model the deformation of the lithosphere, assuming that the system is incompressible. That's the first equation. So we assume that the divergence of the velocity field is null. For the conservation of momentum, we assume at long term that we have no inertia. And we assume that the viscosity linked to the stress field linearly, assuming it's a Newtonian fluid. So we do the assumption that the change in volume is small, and then we apply only the change in density related to the temperature only by changing the density in the momentum equation, but not in the equation, so that we call the Boussinesq approximation. On these three, and then it's coupled to its transport equation. On this field, basically density and viscosity that help to actually reproduce the dynamics of the system and can be used to actually track the topography evolution. So in this presentation, we show a case where we solve this equation in 3D. And this is the setup. We have a damage zone. So it's a large scale model. So it's 1,200 kilometers in the north-south direction and 2,400 kilometers in the east-west direction. I will only focus on this setup in this presentation. So we have a damage zone, which is oblique, 62 degrees, quite similar to the equatorial system. And we have three shear zones, inherited weaknesses, which are parallel to the direction of extension on a line between them. So it's relatively low resolution, but we have scaled the strain weakening parameter that we have strain localization in the model in this system. On the rheology of the crust, you can see the strength profile is a wet quartz rheology for the crust, which means that it's relatively weak crust. So on top of the model, which is a finite element model, we have three surface, and we couple we have a modeling approach to model the fluvial erosion. It's called FastCap. The software is called FastCap. So we solve this equation. So the variation of elevation in FastCap is function of uplift, and the uplift is given by the thermomechanical solution that I just showed before. The erosion is described by the power law, and then we have a diffusion. Yes, we have a diffusion process and a transport process. On the offshore, we have a progradation from the shoreline, and we have diffusion of the sediments.
Okay, Thomas, that's 10.5 minutes.
Yes, thanks. So I'm going to show you some animation in different perspectives. So I'll leave you look at the animation. We have extension, east-west extension. We have uplift of the reef length. We can see the evolution of the catchment through time. And we can see also in the cross-section the formation of the basin, thinning, and then the mantle exhumation phase. So with a different perspective, so now it's a plan view where we can see the evolution of the system. We see that most of the deformation happened perpendicular to the direction of extension. Also, we see that, we see that the reef length extends in the inner corner. So the inner corner is the on-land extension of the transform. So you can see the reef lengths that extend in this domain. We have limited topography or reduced topography along the transform segment. So if we look at another perspective, you can see in the outer corner, which is the part which is in the oceanward direction of the transform, that have survival of quite high topography up to 1 kilometer in the outer corner. And the formation of the catchment mostly occur in the inner corner. So if we look at with high erosion now, we increase the erosion. We see that we have earlier post-reef interland drainage capture in the continuity of the extensional segment, basically the inner corner. And we have much wider oceanward catchments along the extensional segments. So if we do a comparison now with the case with no surface processes on the case with model 1, which was limited erosion efficiency, so we see the localization of the deformations that are happening in the damage zone, and also deformation that localized along the reef flank. When we have surface processes, we see that we don't have much differences between the two evolution. The surface processes, they affect the geomorphology by smoothing the topography. We can see that the damage zone, which is irregular on top, becomes smoother because it's full of flake deposition, continental deposit. And we have reduced reef flank topography because of erosion. What we can see also in the outer corner, in that position, we have little topography here with no surface processes, but when we have erosion, we have this long-term topography in the outer corner, which is a consequence of erosional flexural isostatic response. And then the last observation is that most of this capture of the internal drainage network happen mostly in the inner corner. And it's a consequence, if you look carefully, the topography is a consequence of the lithospheric thinning in the extension of the extensional segment. So if we increase the erosion, so we will say that the model evolution is quite similar, but that finally most of the evolution and timing of the internal drainage capture, which is the difference between the two cases, is mostly controlled by the erosion rate. And the overall structure of the system is controlled by the tectonic evolution, which is a consequence of the inheritance. So the normal faults, they form along the weakest structure, and then they propagate nearly perpendicular of the extension direction in this particular setup. The uplift subsidence and erosion rate along the transform control the catchment evolution on the timing of the drainage capture, especially for the case for the drainage capture in the inner corner on the formation of the long-term topography in the outer corners. And we have ongoing work on the comprehensive sensitivity analysis and model behavior focusing on lithospheric weaknesses, geometry, on surface processes with a paper that will be submit soon. Thank you.
Thanks very much for the great talk. So any questions from the audience? Just raise your hand or put the question in the chat. Yeah. Sasha, is that you? One in the chat. Yeah. Let's see. Okay, yeah. John Baptiste, do you want to say the question or shall I read it out? Okay, I'll read it out. Yeah, so you mentioned that the Romanche was dominantly transpressional while the chain and St. Paul are more transtensional. Did you manage to explain these differences in your model?
Yes. So I show you only one case here, but we have actually did extensive sensitivity analysis on this. I just decided to focus on the case where I call the neutral case, which is inheritance parallel to the direction of extension. If you change the orientation of the inheritance or inherited long transform weaknesses, then you actually form either transpression or transtension at various degrees. I just decided to not show these models here, but yes, you can reproduce those structures.
Great, thanks. So I've got a question about the drainage pattern. Like, how does it compare to real world drainage, I guess, on the margins of Africa and Brazil?
Yes, I don't remember the name of the different rivers, but what I can say is that the drainage pattern that is quite characteristic is the connection of the main rivers in the inner corners. It's something that you see both in Africa and in Brazil. At least for one of the river, it's obvious. For the two others, it's a little bit complication because you have magmatic or other events that superpose to the geometry of the catchment. But so far, the rivers are really old. And we know that the catchment, they survive to the rifts episode. So we have some evidence on, yes, especially for the inner corner capture of the internal drainage network. Yes.
Great. Yeah. And Sasha, you got a question?
Yeah, a quick one. How much do your results change when you change the obliquity? If you think of comparing to other regions in the world, the Gulf of California or the Gulf of Aden, for that matter, does it change your results? Do the rivers evolve in a different way?
So if I change the overall obliquity of the entire reef system, yes, it will. It's a good question. I mean, what? Yes, I mean, it will. Yeah, it will change. If you go to higher, the thing is, if you increase the obliquity much more, you might reach a phase where you actually have a strike slip zone with a pull apart basin along the system. I mean, it will be similar. It depends a lot on the inheritance that you have in your system. So yes, it will change, but that's something I haven't tested with this setup.
Okay, thanks. Maybe something for the next steps.